The next section in the book is going to talk about properties of radicals. This is section 6-2. The essential question will be, how do you simplify expressions involving radicals? The first thing we'll talk about is the product and quotient properties of radicals. So let's say we have the nth root of A and the nth root of B, and these are both real numbers, all right? Well, the first of these properties says that if we've got the nth root of A times B, something like this, that is simply equal to the nth root of A times the nth root of B. So basically we can break up the radical into two sections here. All right, and similarly, if I have the nth root of A over B, where we've got basically a fraction here, so it's the nth root of A over B, again the nth root, this is simply equal to the nth root of A over the nth root of B. So these are the product and quotient properties of radicals. Pretty straightforward, I think. So let's look at some examples and see how we could use these properties. Say, for example, that we've got the square root of 98. Now, if we can find the factors of 98, and if one of those factors is a perfect square, we could ideally simplify this. Well, what is 98 equal to? 98 is simply equal to 49 times 2. So this is equal to the square root of 49 times 2, which is equal to the square root of 49 times the square root of 2, or more simply, 7 times the square root of 2. Similarly, let's say we have the cube root of 81 over 8. So we've got the cube root of 81 over 8. So using the quotient property, I can rewrite this as the cube root of 81 over the cube root of 8. And I can further simplify that by saying the cube root of 81 is simply the cube root of 27 times the cube root of 3 divided by the cube root of 8. Well, that's simply 2. And our final simplification, the cube root of 27 is 3, so this becomes 3 times the cube root of 3 over 2. So here are a couple of examples of how we can utilize these properties of radicals. So now let's discuss what we mean by something being in simplest radical form. An expression is in simplest radical form if the number underneath the radical does not contain a factor that is a perfect power of whatever that radical is. For example, if we have the square root of something underneath the square root radical sign, there is no factors that are perfect square roots. So that is one case. The other case is that you cannot have a radical in the denominator. You must rationalize it, okay? Now, so let's explain these two things by looking at some examples. So let's look at a case where we have the square root of 75. So we've got the square root of 75. Well, 75 is not a perfect square, but 75 has 25 as a factor, and that is a perfect square. So the square root of 75 is simply equal to the square root of 25 times 3, which is equal to the square root of 25 times the square root of 3, or simply 5 times the square root of 3. Okay, now this is in simplest radical form. All right, another example might be if we had 15 over the square root of 3. So let's assume we got 15 in the numerator and the square root of 3 in the denominator. Well, we know it's not in simplest radical form if we got a radical in the denominator. So how do we rationalize it? Okay, in order to rationalize it, we are going to have to multiply this by the square root of 3 to get rid of the radical in the denominator. So I have to multiply the denominator by the square root of 3. But whatever I do to the denominator, I also have to do to the numerator. So I have to multiply the numerator by the square root of 3. So what does this give me? This simply gives me 15 times the square root of 3 in the numerator, and the denominator, square root of 3 times the square root of 3 is simply 3. Now I can further simplify this by dividing 3 into 15, and our final simplified answer is 5 times the square root of 3. Now finally, we've got two theorems that are often useful in numerical work with radicals, and we will discuss those right now. The first of these is Theorem 1. And Theorem 1 simply states that if you've got the square root, let's see. How do I want to say this? The n times p root of b, that is equal to the nth root of the pth, if you will, root of b. So what do we mean by that? Let me give you an example. Let's say we've got the fourth root of 100. Well, I can rewrite that as the square root of the square root of 100. Well, that inner radical, the square root of 100, is simply equal to 10. So this is equal to the square root of 10, which is simpler, and we can plug that into our calculator and get a numerical answer. Now, theorem 2 simply states that if we've got the nth root of b to the m, this is equal to, inside parentheses, the nth root of b, and that whole thing raised to the m. Okay, now I would like you to go to page 267 in your textbook and do oral exercises number 1 through number 4 and post your answers in the drop box. These are simply to tell whether each radical is in the simplest form, so you answer either yes or no.